Hilbert's 10th problem is the 10th on the list of Hilbert's problems of 1900. Its statement is as follows. Given a Diophantine equation with any number of unknown quantities and with rational integral numerical coefficients, to devise a process according to which it can be determined in a finite number of operations whether the equation is solvable in rational integers. It took many years for the problem to be solved with a negative answer. Today, it is known that no such algorithm exists in the general case because of the Matiasevich (MDRP) theorem that states that recursively enumerable sets are equivalent to Diophantine sets. This result is the combined work of Martin Davis, Yuri Matiasevich, Hilary Putnam and Julia Robinson, which spans 21 years. With Yuri Matiasevich completing the theorem in 1970. Formulation. The words process and finite number of operations have been taken to mean that Hilbert was asking for an algorithm. The term rational integer simply refers to the integers positive, negative or 0, 0, plus or minus 1, plus or minus 2. So Hilbert was asking for a general algorithm to decide whether a given polynomial Diophantine equation with integer coefficients has a solution in integers. Such an equation can be put in the form where P is a polynomial with integer coefficients. The answer to the problem is now known to be in the negative. No such general algorithm can exist. Although it is unlikely that Hilbert had conceived of such a possibility before going on to list the problems, he did presciently remark, "Occasionally it happens that we seek the solution under insufficient hypotheses or in an incorrect sense, and for this reason do not succeed. The problem then arises. To show the impossibility of the solution under the given hypotheses or in the sense contemplated, the work on the problem has been in terms of solutions in natural numbers rather than arbitrary integers. But it is easy to see that an algorithm in either case could be used to obtain one for the other. If one possessed an algorithm to determine solvability in natural numbers, it could be used to determine whether an equation in unknowns has an integer solution by applying the supposed algorithm to the 2n equations. Conversely, an algorithm to test for solvability in arbitrary integers could be used to test a given equation for solvability in natural numbers by applying that supposed algorithm to the equation obtained from the given equation by replacing each unknown by the sum of the squares of 4 new unknowns. This works because of Lagrange's four-square theorem, to the effect that every natural number can be written as the sum of 4 squares. Diophantine sets. Sets of natural numbers, of pairs of natural numbers that have Diophantine definitions are called Diophantine sets. Diophantine definitions can be provided by simultaneous systems of equations as well as by individual equations because the system is equivalent to the single equation. A recursively enumerable set can be characterized as one for which there exists an algorithm that will ultimately hold when a member of the set is provided as input, but may continue indefinitely when the input is a non-member. It was the development of computability theory that provided a precise explication of the intuitive notion of algorithmic computability, thus making the notion of recursive enumerability perfectly rigorous. It is evident that Diophantine sets are recursively enumerable. This is because one can arrange all possible tuples of values of the unknowns in a sequence and then, for a given value of the parameter, test these tuples, one after another, to see whether they are solutions of the corresponding equation. The unsolvability of Hilbert's 10th problem is a consequence of the surprising fact that the converse is true. Every recursively enumerable set is Diophantine. This result is variously known as Matiasevich's theorem and the MRDP theorem. Because there exists a recursively enumerable set that is not computable, the unsolvability of Hilbert's 10th problem is an immediate consequence. In fact, more can be said. There is a polynomial with integer coefficients such that the set of values of for which the equation has solutions in natural numbers is not computable. So, not only is there no general algorithm for testing Diophantine equations for solvability, even for this one-parameter family of equations, there is no algorithm. History. Applications. The Matiasevich (MRDP) theorem relates two notions, one from computability theory, the other from number theory, and has some surprising consequences. Perhaps the most surprising is the existence of a universal Diophantine equation. There exists a polynomial such that, given any Diophantine set, there is a number such that this is true simply because Diophantine sets, being equal to recursively enumerable sets, are also equal to Turing machines. It is a well-known property of Turing machines that there exist universal Turing machines, capable of executing any algorithm. Hilary Putnam has pointed out that for any Diophantine set of positive integers, there is a polynomial such that consists of exactly the positive numbers among the values assumed by as the variables range over all natural numbers. This can be seen as follows. If provides a Diophantine definition of, then it suffices to set so, for example, there is a polynomial for which the positive part of its range is exactly the prime numbers. Other applications concern what logicians refer to as propositions, sometimes also called propositions of Goldbach type. These are like the Goldbach conjecture, in stating that all natural numbers possess a certain property that is algorithmically checkable for each particular number. The Matiasevich (MRDP) theorem implies that each such proposition is equivalent to a statement that asserts that some particular Diophantine equation has no solutions in natural numbers. A number of important and celebrated problems are of this form. In particular, Fermat's last theorem, the Riemann hypothesis, and the four-color theorem. In addition, the assertion that particular formal systems such as Peano arithmetic or ZFC are consistent can be expressed as sentences. The idea is to follow Kurt Gödel encoding proofs by natural numbers in such a way that the property of being the number representing a proof is algorithmically checkable. Sentences have the special property that if they're false, that fact will be provable in any of the usual formal systems. This is because the falsity amounts to the existence of a counterexample which can be verified by simple arithmetic. So if a sentence is such that neither it nor its negation is provable in one of these systems, that sentence must be true. A particularly striking form of Gödel's incompleteness theorem is also a consequence of the Matiasevich (MRDP) theorem. Let provide a Diophantine definition of a non-computable set. Let be an algorithm that outputs a sequence of natural numbers such that the corresponding equation has no solutions in natural numbers. Then there is a number which is not output by while in fact the equation has no solutions in natural numbers. To see that the theorem is true, it suffices to notice that if there were no such number, one could algorithmically test membership of a number in this non-computable set by simultaneously running the algorithm to see whether is output, while also checking all possible tuples of natural numbers seeking a solution of the equation. We may associate an algorithm with any of the usual formal systems such as Peano arithmetic or ZFC by letting it systematically generate consequences of the axioms and then output a number whenever a sentence of the form is generated. Then the theorem tells us that either a false statement of this form is proved or a true one remains unproved in the system in question. Further results. We may speak of the degree of a Diophantine set as being the least degree of a polynomial in an equation defining that set. Similarly, we can call the dimension of such a set the least number of unknowns in a defining equation. Because of the existence of a universal Diophantine equation, it is clear that there are absolute upper bounds to both of these quantities, and there has been much interest in determining these bounds. Already in the 1920s, Thoralf Skolem showed that any Diophantine equation is equivalent to one of degree 4 or less. His trick was to introduce new unknowns by equations setting them equal to the square of an unknown or the products of two unknowns. Repetition of this process results in a system of second-degree equations. Then an equation of degree 4 is obtained by summing the squares. So every Diophantine set is trivially of degree 4 or less. It is not known whether this result is best possible. Julia Robinson and Yuri Martiusevich showed that every Diophantine set has dimension no greater than 13. Later, Martiusevich sharpened their methods to show that 9 unknowns suffice. Although it may well be that this result is not the best possible, there has been no further progress. So, in particular, there is no algorithm for testing Diophantine equations with 9 or fewer unknowns for solvability in natural numbers. For the case of rational integer solutions, the four squares trick shows that there is no algorithm for equations with no more than 36 unknowns. But Jiwei Sun showed that the problem for integers is unsolvable even for equations with no more than 11 unknowns. Martin Davis studied algorithmic questions involving the number of solutions of a Diophantine equation. Hilbert's 10th problem asks whether or not that number is 0. Let and let be a proper non-empty subset. Davis proved that there is no algorithm to test a given Diophantine equation to determine whether the number of its solutions is a member of the set. Thus there is no algorithm to determine whether the number of solutions of a Diophantine equation is finite, odd, a perfect square, a prime, etc. Extensions of Hilbert's 10th problem. Although Hilbert posed the problem for the rational integers, it can be just as well asked for many rings. Obvious examples are the rings of integers of algebraic number fields as well as the rational numbers. There has been much work on Hilbert's 10th problem for the rings of integers of algebraic number fields, basing themselves on earlier work by Jan Denef and Leonard Lipschitz and using class field theory. Harold N. Shapiro and Alexander Schlepantoke were able to prove Hilbert's 10th problem is unsolvable for the ring of integers of any algebraic number field whose Galois group over the rationals is abelian. Schlepantoke and Thanasis Fidus obtained the same result for algebraic number fields admitting exactly one pair of complex conjugate embeddings. The problem for the ring of integers of algebraic number fields other than those covered by the results above remains open. Likewise, despite much interest, the problem for equations over the rationals remains open. Baru Mazur has conjectured that for any variety over the rationals, the topological closure over the rails of the set of solutions has only finitely many components. This conjecture implies that the integers are not Diophantine over the rationals, and so if this conjecture is true, a negative answer to Hilbert's 10th problem would require a different approach than that used for other rings.